Okay, so let's proceed with another example of approximate analysis of building frame using beam stiffness matrix. This time we will be solving frame with sway. So how do we know a frame has a sway? Of course, you have lateral load and there's no lateral restraint that will prevent the sway. And also, if you have unbalanced loading, that could cause a sway. So the given is a portal frame with a uniform load on top and a 40 kilonewton lateral load, 10 meters by 10 meters, and we have an elasticity of 200 gigapascal and inertia of 300 times 10 raised to 6 millimeters to the fourth. Again, this is the coding that we will be using. So this is number 1, number 2, number 3. So our degree of freedom 1 is oriented to this direction for the lateral or for the movement in this lateral direction, and the rotation degrees of freedom number 2, degrees of freedom number 3 for the lateral sway here, and rotation degrees of freedom 4. And since we are considering the same lateral displacement, so the degrees of freedom code here is also 3 on member 3, and we have a rotation of number 7. Notice that my coding is from bottom to top. That is my direction. Okay. For the beam number 2, we have a degrees of freedom number 5, and rotation is to be consistent with number 1. It's also number 4. And for the vertical displacement number 6, and rotation is 7. That's why it's also 7 here to be consistent. Since we already use 7, next code is 8 here, and rotation is 9. Okay. So the most important thing here is you need to make sure that the code for the lateral displacement is the same. Okay. So this is our K1, K2, K3, and getting all those codes for each element stiffness matrix. So K1 is 1, 2, 3, 4. K2 is 5, 4, 6, 7 here. K3 is, take note again, be starting from the bottom, 8, 9, 3, 7. So 8, 9, 3, 7. Okay. Now, how many degrees unknown displacements do we have? So we said that we have a lateral displacement, so that's 1, and a rotation on this joint, so 2 and 3. Because we have fixed supports here, there's no displacement here. So we have 3 unknowns, 3 displacements, and the code for those 3 unknown displacements are 3, 4, and 7. So 3, 4, and 7. And to get the BU and BB matrix, this is the location. What's the location of 3 and 4, the encircled numbers here? So third and fourth element. So this one. What's the location of 4 and 7? Second and fourth. Second and fourth. What's the location of 3 and 7? Third and fourth. Okay. Now let's consider the BB matrix, the destination. For this 3 and 4, their destination is on 1 and 2, right? So 1 and 2. For 4 and 7, its destination is 2 and 3. 2 and 3. For 3 and 7, its destination is first and third. So 1 and 3. Okay? Now for the QF, because we have a uniform load acting on member 2, QF is 90, 150, 90, and negative 150. So basically, it's a fixed uniform load. So the formula is WL squared over 12 for the moment. And for the reaction, it's basically WL over 2. Okay? And negative sign here. And don't forget to be consistent with the code 5467 for member 2. 5467. For the PF, we will only get the forces corresponding to our S matrix 347. So you don't have QF on code 3. For degrees of freedom 4, we have 150. For degrees of freedom 7, we have negative 150. And how about the P vector? Because we have an applied load, okay, here. So we have an applied load at degrees of freedom 3, which is 40 kilonewton. That's it. Okay, 40 kilonewton. So P minus PF, get the value. So operating this 2 matrix, you will have this final load vector. Okay. So basically, that's it. And this is the corresponding SMAT. Okay, so this is the corresponding SMAT. So the null matrix S4 3 by 3 because the size is 3 by 3. And these are the length vector, inertia vector. Made this 3 because the SMAT is, this code is programmed for times 10 raised to 9 millimeter to the fourth inertia. So convert 300 becomes 3 times 10 raised to 9. Okay, next is, this is the transformation matrix required for column, for beam, and for column. And to get the global stiffness matrix, transfer T transpose K log half times T to get the global. And this is the code for generating S. And PPF, just this is this one. So 40, negative 150, and okay. And this is the S matrix we generated from this program. And these are the corresponding displacement. So 3.96. Remember, the code is 347, right? 3 is the sway. Code 3 is the sway. So 3.96 millimeter. So let's check. Okay. I have summary already here. Where is that? I haven't checked. So sway. So displacements and view, front view. Okay. So this one. So 39.6 767. Maybe I just have to correct the inertia. Okay, so 39 mm displacement. So I corrected the code because I forgot. This is only 300 times 10 raised to 6. So 300 times 10 raised to 6 to convert into times 10 raised to 9. So 1, 2, 3. So I should have input 0.3 instead. Okay. And this is it. I corrected this 0.3, and this is now the displacement, 39 mm. Okay, so to get the member forces, so you already know how to set up the displacement because for V1, so this is 1, 2, 3, 4. So this D1 is the sway and D2 is the rotation. For element member number 2, this is the rotation here, and this one is the rotation on the other end. For member 3, so I told you that my orientation is from bottom to top. So we have 0 displacement at the bottom, and D1 again is the sway, D3 is the rotation. Okay. And to get the member and force for 2, the formula is k times the displacement matrix plus the qf, because you have an applied load along the span, and your qf vector is this. So your q2 is this. So I have this pasted here already, this one. Okay. So number 2, 72 is this one. 14 is the moment. 107 is the reaction. Vertical, negative 185 is the moment. For member 1, negative 5 is this. 64 is the moment. 5 is reaction here. And 14 is the moment. So this will cancel out. For member 3, 35 is this. 164 is this. 35 is this, and 185, such that this moment will cancel out. Okay, so, and this is the corresponding STAAD file for that. So to get the reactions, these are the reaction 5 and 64. Okay, then for node number 4, 35 and 164. So that's it. 35 and 164. Okay. So this justifies that using just a beam stiffness matrix, we can approximate uh, the 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 forces or the behavior of a building frame. Okay. And this is further justified because remember, in our code, like for concrete, we maintain a strong column weak beam. So that means your column will be much greater than the beam. So So that means it could carry that much axial force. So we ensure that the column is stronger, okay? Such that an axial deformation, for especially in a typical low-rise building, will not be that much. Okay? And this is our assumption in this problem, in this approximate analysis of building frame. And that assumption uh, makes it uh, makes it makes it true that using beam stiffness matrix will be enough to approximately analyze this building frame, even multi-story building frame, okay, using just a 4 by 4 matrix. Okay, so let's how about the member forces? So let's see. I'll minimize this and proceed with our free body diagram here. This is taad. So to quickly get the member forces for each member, so simply double click. Under beam results, double click, and shear bending. So you're looking at the bending moment now. So 14, so this is 14, 185, so this is 185. And let's look at the shear. We have 72 going up, and then 107, 107. Okay, how about member one? So we have bending of 64 here and 14 on the other end. And for the shear, 5, both 5. Okay. And for member 3, double click. So the shear is 35. Okay. And the bending is 164, 185. Okay.